Hi, this is Dr. Liu. So let's have a look at the data analysis for the RLC lab. So on the left side, I have the menu open. The right side, I have data and analysis. So I intentionally blocked most of my data because you're not supposed to be copying these data. You're supposed to analyze your own data. So let's take a look at the data. We have frequency, we have the resistors voltage, inductors voltage, and also capacitors voltage. They all have their labels and the units. And starting this column is a calculation. So let's first follow uh, the lab manual. So we want to plot resistors voltage versus frequency. So let's scroll to the right. So here's the resistors voltage versus frequency. You can definitely see there's a maximum there. And the maximum that was found experimentally was at 100.7 hertz. So that was by varying frequency by 0.1 hertz at a time carefully. So we can see there's a maximum. If we go further beyond that 100 hertz, we can see the shoulders coming down, just like the left side going up. So that. It should be identifying this, well, that was identified by experiment. And then part two is to calculate this frequency in theory. So the theory value L times C. L was 1 Henry for all the inductors. The C may vary, but only very slightly. 2.24, 2.25 microfarads. So that's the C. And if you calculate this 1 over 2 pi square root LC, you get a theory. So there's 1 over 2 pi square root of L times C. So that gives you 106.3. So they're very close. We should calculate a relative difference, or we rather say it's relative error. So subtract the 2, divide by the theory value, that gets you 5%. So this is relative error. We don't have a relative uncertainty here to draw a conclusion, even though I think we can estimate some relative uncertainty to be maybe around plus minus at most 1 hertz, because if you think about it, if you change 1 hertz, the voltage can drop. So you can see it's no longer maximum, but we're not expected to analyze that. So we can't really draw a positive or negative conclusion. We'll just say that we have a relative error of 5%. And part three, we have Excel calculate the current for each frequency using current equals voltage of across a resistor over resistance. So here, let me scroll to the left. So this is that column. So the calculation is the voltage across the resistor over the actual resistance that we measured with our multimeter. So that's the actual resistance. I use the dollar sign here. I actually don't need dollar sign in front of J. The dollar sign in front of 1 will fix the reference to this J1 cell. Otherwise, my next cell will refer to J2 cell, and the J2 cell isn't this resistance anymore. Okay, so if you open up one of these, yeah, the 1 is fixed, so always referring to the same cell, same row 1, even though the voltage keeps increasing to B3 and B4, right? So that's just a trick of the formula, how to enter it. So this is calculated, and okay, so have this calculated, and then also look at the manufacturer's value, which is supposed to be 470 ohms with a 5% tolerance. So is your measurement within that tolerance or consistent with the tolerance? So let's see. So the manufacturer's value is 470, and this is the actual value 469.4. So the relative error of the resistance is 0.1%, which is less than the factory's promise tolerance of 5%. So this is consistent. We're actually getting a better deal than the factory promises of 5%. we get quite a nice value, close to 470. Okay, so that's part 3 here. So part 4 we'll calculate more. So we have Excel calculate expected voltage drop across the capacitor. So let's do that. Let's take a look at it. The expected voltage drop, I had this VC theory here, right, on the right side. And it's supposed to be calculated as the current, which I just calculated based on the resistor. So let's scroll to the left. Current that I calculated based on the resistor's voltage over resistance. So that's that current, and divide by 2 pi frequency and capacitance. The capacitance is this value. So let's see if that's the right combination. Okay, so I have E2, which is current, the one on the top, and divide by 2 pi. A2 is the frequency right here, and 2 pi F, and then also divide by C, J is 3. So I guess I don't need to fix J, but I do need to fix the 3, so the reference is always to J row 3 instead of keep going further down. Okay, that shouldn't change anything. So let me open up another one as an example. See the E4 is the current times 2 over 2 over pi, then over the frequency, and over J3, the same exact capacitance reference at all different rows. So that is a calculated voltage across the capacitor. We also measured the voltage across the capacitor, and it looks like they're very similar. So you need to plot it. So have this calculated, and it says comment generally how the measured and the expected compare throughout the data set. It will be difficult to do such a comment without plotting. So you're required to plot them. So here is the plot. So I plotted out both the theory curve, which is the orange dots, and also the experimental data, the blue dots. The orange and the blue are so overlapping with each other, I had to make the orange dots smaller to show there's actually blue dots underneath it. So if you really want to do that, you need to right click on the orange dot and then go, let's see, for my data series, and then go to fill and line, and under markers, and you can go to marker option. Instead of automatic, make sure it's built in, and you have the dots, and then you reduce the size from 5 to 3. Another way to show this is you can have a different marker shape. Say if you have, I want to see if there's anything that's like a cross. I guess there's no crosses in here. That's unfortunate. I thought there might be a cross here. So let's use a triangle, and we can restore to the shape size number 5. So this also shows that the two are overlapping because they're different shapes. So long as you're plotting them, I'm not requiring you to make them actually that visible against each other. So I just need the data plotted. So the plot is frequency as horizontal, voltage is vertical. So this needs to be plotted, and separately there's another plot. So if you open up, see the data, there are two plots. This one is the VC versus the frequency. The other is the theory VC versus frequency. And I named it such so that I have a legend that shows which one is which. Okay, and the same thing also need to be done with the inductor's voltage. So the inductor's voltage is a bit more difficult to theorize, is right there. And we measured the inductor's voltage. So let's scroll to the left. This is the inductor's voltage column. So inductor voltage theory, if I open it up, okay, a little more difficult, right? So current, then resistance squared. This is inductor's own resistance. So that's a 44.7 right here I have. I don't know why I have so many sig figs. I'm going to take care of that. And then square root and J2, I guess I don't need to fix the J, I need to fix the 2, so this reference doesn't go to the next row and such. So this R squared, J2 squared, and then there's a 2 pi F and L. So parentheses 2 pi, this is F frequency, purple, L is the inductance, is 1 Henry, and then square that, finish the square root. Let's make sure the formulas all have the optimal reference, even though the original version works. So this is too many sig figs. I think we were able to get 3 sig figs, if I remember right. Okay. So the theory curve of the inductance voltage, the actual measured voltage, if you compare the two, these two are more different than the theory and experiment for the capacitor. So let's look at the plots. So here are the plots. Again, I was using different sized let's see, select data, format data series, different size data labels. Maybe I should just use different shapes instead. So triangle, same size. Okay, so same size also hints the same uncertainty. I think that's a good thing. We use the same multimeter, right? So we should have same sizes. So you can see the theory curve goes up and the experimental curve goes up. There's a small amount of a discrepancy in between the two. So that's what we can say in terms of comment. You can say that the if the two curves trace each other, how closely they trace each other, that will be your conclusion. In my conclusion, only one trace very closely to each other, and the other one visually at the maximum there is let's see 0.9 0.89 0.99. So at the maximum there's a separation up to about 0.1 volts. So that would be what I would comment on the data, because you can't really comment that without having some visualization. Make sure all these required elements are here, the labels, and there's also a title for each. So that's that. And then there's a second one, next one here, part 5, have Excel calculate the phase angle. So this phase angle is this. Let's scroll back to see the phase angle. This is what I finished plotting. So again, the horizontal axis is frequency, and the vertical axis is phase angle. So from minus 90 degrees roughly to 0 degrees at resonance, and then to positive angles. So this tells you um, voltage is leading current here above resonance, and below resonance voltage lags from current. And the way to calculate this is you need to take the inverse tangent of this function. So let's see how I calculated my phase angle. Okay, so I have a degrees because the arctangent or inverse tangent respond with a reading angle. So you do A tangent and C2 D minus D2 over B2. So C2 is the inductor's voltage, measured voltage, and the D2 is the capacitor's measured voltage, and the B2 is the resistor's measured voltage. You go with measured instead of the theory. So with all that in arctangent, it gives out an angle in radians, and then you use the degrees to turn that into degrees. You don't have to follow these. Um, this is more intentional and more clear what you're trying to do. Find the angle, turn it into degrees. So with this, you have all the different angles here, and you can plot this out and have a conclusion. So that should give you everything that you need. So again, there are 4 plots. Have it calculated is not enough. You should plot it out just to see the trend, right? So 4 plots. One of them is the voltage across a resistor as a function of frequency. That shows there's a resonance around 100 hertz. And another one is the theory versus experiment of the inductor's voltage. And you can comment on how close they trace each other. And another one, a similar one, is the voltage across the capacitor, theory versus experiment. And then the last one is the phase angle experiment. This is from different frequencies at different phase angles. And you're also expected to draw some, well, not draw a conclusion, to calculate something. Relative error of the resistor you measured versus the manufacturer's value. And also there's this one more thing. It is the relative error between the experimental resonant frequency and the theory resonant frequency.